Hello, I would like to introduce the structure of the transistor and three current formulas that are mainly used for transistors. First of all, the table of the contents is as follows. Let's take a look at the role of the transistor based on the name of the transistor, and then let's look at the working principle of MOSFET based on the structure of the N-channel transistor. Through this, after understanding the degree of the transistor, I will introduce the three current formulas in turn. Transistor is a compound word of transfer and resistance, which literally means to change the resistance. Freely changing the resistance means that the current can also be freely adjusted, and the actual transistor can play the same role as amplifying the current and the switch that make the on and off action. This picture is the structure of N-channel MOSFET, a type of MOSFET. In the case of N-channel MOSFET, a P-type semi-transistor with a lot of tangles is used as substrate, and on the top of insulating materials, oxide and metals rise form a gate, and on the both sides of this gate, it made up by N-type doped source and drain with many electrons. If the electrode of the substrate is 0 voltage and the minus voltage is amplified to the gate electrode, if you first look at the gate electrode, the hole, which is the carrier of many of P-type silicon, is guided by the minus voltage and the holes gather on one side. This is called an accumulation state, and in this case, the current cannot flow between N-type semi-complex. Simply put, the holes are accumulated in a small space, so even if the electrons try to go over, they merge with the holes and disappear, so the electrons can't go over. Conversely, when plus voltage is applied to the gate electrode, the holes run out, creating a state of deprivation between the N-shaped semiconductors. At this time, if plus voltage is applied more strongly to the gate electrode, very few minus electrons that exist in P-type semiconductor will gather at the top. And if these electrons continue to gather, these electrons will form a tunnel-like length, and an electric current will flow between the N-type. In the N-channel MOSFET, these layers are used to make electrons flow. Therefore, when a voltage above a certain voltage of the gate is applied, the current flows to conductors, and the voltage at this time is called the gate voltage, and the current flowing from the source to the drain is called the drain current. We call this ID. This drain current increases in proportion to the drain voltage. Now, let's use the Shockley diode equation to derive the transistor current formula. To understand the transistor and the current flowing from it, we can first use the Shockley diode equation to derive an equation for the length of the current flowing through the collector part of the transistor to make it simple. Next is the Shockley diode equation. This Shockley diode equation does not end in describing the diode and can be used extending the current formula of the transistor. Expression can be transferred as follows. It can be thought of by replacing the diode current with ID, the current flowing through the collector of the transistor, by changing the diode voltage VD with the voltage at the base and emitter of the transistor. Now, I'm going to introduce this formula. The table above shows the circuits of the transfer and diodes. As you can see in the table, both of these elements are based on semiconductors, so you can see that their structure are quite similar. Therefore, the current equation of the two elements are compatible, so you can understand the current equation of the transistor through the Shockley diode equation. To derive the diode equation described earlier, You can first take a large frame in the formula of y equal e squared x and build one by one based on this graph. So let's take a look at the feature of the y equal e squared x graph. The following feature of a graph diode voltage characteristic and an exponential graph in the form of y equal e squared x. You can see that the variation of these two graphs are quite similar. If you adjust the index function of a well, you will be able to make it similar to the graph in the forward voltage portion of the diode graph. To adjust the exponential function graph well, it is necessary to understand the characteristic of the exponential function graph. As you can see by comparing each of above graphs, the exponential graph can be seen that the graph becomes more and more rapidly as the base of the exponential graph grows. Comparing the above graph, you can see that larger exponential of the exponential function, the sharper the graph, the similar to the previous situation. Based on this basic concept, you can take the bone of the diode's equation. Step 1. The diode voltage graph goes through 0.0 as shown in the previous diode voltage characteristic graph. So, y equal e squared x graph descends by 1 in the direction of the y-s to pass 0.0. Step 2. One of the features of the diode graph from a certain voltage or more to rapidly increasing features should be implemented. Among the exponential function graph properties we looked at earlier, we multiply the x value of y equal e squared x minus 1 using the characteristic that increases the slope of the graph as the exponential function increases. This index x also sets the slope, but it also serves to set the value so that the current can flow rapidly at about 0.7 voltage. Therefore, it is not a random set of value, but an expression should be put based on the theoretical background. E equal QV formula is also included in Physics 2 subject, so the above expression induction is fully understandable, so I will skip the explanation. Step 3. The diode voltage characteristic graph shows a form of a sharp increase in the graph until 0.7 voltage after 0.0, and then a sharp increase after this voltage. To correct this with an exponential function graph, I will explain the characteristic of the exponential function graph. The parts shown above the diode voltage characteristic graph, we can assume that the current flows constantly because the tilt of the current is very small. It is not very constant, but almost constant. So, this state of small but constant flow is saturated. So, you can think that does not move. The following graph shows that multiplying a natural index function by a small value can delay a rapidly increasing value. This is similar to the nature of the delay coefficients that adjust the delay. Therefore, multiplying a very small value of a by y equal e squared x minus 1 can significantly delay the graph of the exponential function. So, y equal a times e squared x minus 1 function can be made. So, you can put Is, the reverse saturation current, in A to complete the equation. The final completed diode current equation is followed as like this. As I described earlier, this can also be changed by finding the collector current of the transistor, which is complete by changing the diode current to the collector current. So, diode voltage per thermal voltage to thermal voltage per residual voltage between the base and emitter. The finished function is like this. Based on this process so far, if you have a somewhat simple understanding of transistors, you can derive the current formula of the widely used MOSFETs in earnest. The picture above is a picture of the structure of N MOSFET. NMOS is an N-type semiconductor doped MOSFET. There are three equations that you need to know first to drive the current formula of MOSFET. In the above equation, W means widened the MOSFET, Q means the amount of charge, and V means the speed of the electrons. First of all, you need to understand how these expressions come out. With a voltage on both sides of the MOSFET, the electron inside the transistor moves from the source to drain to create an electric current, and the current is called Ix. This current is determined by how many electrons there are and the speed of the electrons. The current is constant, so X comes out the same no matter what the value you choose. So, if you change Ix to ID, ID means current following in the drain. The same exists above. Formula 2. This expression is derived from the expression that Q equals CV. This formula also introduced in Physics 2 subject. In the above equation, C is an electrical capacity, so you don't need to deal with it in detail. And to explain the voltage part in detail, Vx is the voltage at X position and Vt is the voltage consumed by forming the voltage itself. The reason why Vx is represented as a function is that the more voltage increases from the source to drain, so it can be represented as a function for X. The more electrons go to drain, the amount of electrons increases. Because the electric field receives electricity, the electrons accelerate and the speed of the residue increases. Thus, the closer to the drain, the amount of the electrons decreases. Formula 3. This equation is the speed formula of electrons. It takes too many underlying concepts to induce this formula, so you have to simply borrow it and explain it. However, what we can think about here is that this equation E is an electric field, which is differential of Vx electrical position energy. So, we can derive the above equation. If you substitute Formula 2 and 3 into Formula 1, it as follows. Since the purpose is to find the current of the total length L by integrating the current of a certain part X, the two sides of this equation are integral to X. To clean up the right side of the equation above, we substitute Vx with V and integrate. The above expression holds only in the linear region. Separation region is a region where Vds is greater than or equal to Vgs minus Vt. It is an area where the vertical electric field Vds by gate voltage and the horizontal electric field Vgs minus Vt by drain voltage are offset against each other and the electric field is not formed. In addition to this area, the area where an electric field can be formed as linear area. Through this process, a formula is obtained to obtain the current flowing through the drain. Finally, I will finish by finding effective value indicating the amount of current that can actually be used when the AC power is connected to the transistor. The two graphs above show the current at each DC power source and AC power will be connected respectively. DC power has the same maximum effective and average value, but all of these different for AC power sources. Therefore, to find the value that can be practically used when connecting AC power, it is to find the effective value. Each is the value that converts the alternating current to direct current when the amount of electricity and the amount of alternating current is the same. The table above shows the DC-AC power connection circuit and the power consumption when connecting to the power source. In order to know the effective value of AC power supply, the P of the AC power supply and the direct current power supply must be the same. P means the power consumption. Since the alternating current graph is in the form of a sine wave, it should be represented as a function in which the currents change over time. In the above equation, t is the time. So, you can set these equations and induce the IRMS of direct current through it as follows. RMS means root mean square, which is dividing the area by time, so it means the average of power. If the maximum current of the graph in the form of the sine wave of alternating current circuit is called Im, the equation of the alternating current power is as follows. Therefore, the effective value of the AC power supplies is as follows. The things I've induced so far have given an understanding of how transistor works and its structure. Thank you for listening to my presentation.